Well, this is an interview on July 12th at MIT with Barbara Liskov. I'm David Brock from the Computer History Museum. Thank you very much for doing this again.
Sure.
And as I kind of prefigured, I'd like to begin with some sort of overview questions for our museum audience.
Okay.
And one is a question I expect you get asked. It wouldn't be the first time you were asked this question of how you would describe your contributions to computing to someone who isn't an expert or necessarily deeply familiar with computing.
It's actually very hard to explain what I do to a non-computer scientist because my work is in the underpinnings of how software is developed and how systems are built. And so I got interested early on in the problem of how to construct software systems so they actually worked. And that led to the invention of something I call data abstraction, which is one of the major ways that people develop software today. And basically, this work has to do with breaking programs up into modules that can be built independently, reasoned about independently. And in that way, it relates to all engineering disciplines. Every discipline has some way of modularizing whatever it is that's being built. What's unusual about software is there are no constraints. So all you have is a computer. There's nothing in that computer that constrains how you organize things at all. So it all had to be invented. And really, the way it's done is quite closely related to mathematics and how theorems are proved. In theorems, you have lemmas. Those are like modules. You reason about the correctness of some hypothesis depending on definitions that are lower down. You break the problem up into pieces, and this is really the way that software is built as well. In addition to that work, I got interested in the problem of distributed computing in the days when it was more like a dream than a reality. And I did a lot of work there. A lot of it still had to do with how programs are structured, but I also got interested in the problem of how to produce storage systems that didn't lose information in the presence of attacks or hardware failures or other things like that. And that led to various replication. The way you do it is through replication by having multiple copies of the information, but it's tricky because you have to make sure that those copies are all in sync in spite of whatever is going on. The early work had to do with just failures because that was the big problem in the 80s when I did that work. And then in the 90s, we started working on attacks, malicious attacks, which are a big problem today. And that led to a couple of protocols that are very basic in the way that storage systems are organized. So I would say those are the sort of main things that I did.
And if I can ask a follow-up question about the data abstraction. When I was talking about your work and data abstraction, abstract data types, when I was talking about it with a few of my colleagues who have a background in programming and the history of programming languages, it really seemed to me that this approach of data abstraction has become so widespread that it's today, in today's world, that it's almost difficult for people to imagine a time when this wasn't the practice.
Yeah.
Is that fair to say? Is that what you
Absolutely. When I got the Turing Award it was 2009, the first thing I discovered was that my students had no idea that there was a time before. And another thing that happened, and I wasn't working on programming languages and data abstraction at the time. I'd really stopped thinking about it because I was focused on this work on storage systems. Another thing that happened was my husband was looking at all the chatter on the internet, and he came across this quote that said, "What did she get that award for? Everybody already knows this." And I thought that summed it up very nicely. Yes.
Well, that's really interesting. So it really this data abstraction, this way of achieving modularity,
Yeah.
might you say, in software, is really, it's kind of the method or the engineering approach that people take for building all the software that impacts us in so many different ways.
Right.
Is that kind of a fair?
That's true. It became the way people build software. And it wasn't my work alone. I mean, there were other people working in program methodology. I just happened to identify this idea of abstract data types at a time when, looking back, I could see it kind of floating around waiting to be picked up. And my work also, the other stream of research was the work that was being done by Alan Kay
Yes.
on Smalltalk, and those two pieces came together. There, I think they were much more interested in, at the time, in inheritance and how you could have a subclass that would be implemented just making a few changes to what was going on in the superclass. Whereas I tended to think about it much more in terms of what is the meaning of a module. So I was thinking about writing specifications and the sort of mathematical understanding what was going on. You have to put the two things together to get the whole picture.
Right.
So this is what object-oriented programming turned out to be.
Thank you. The next question I had was if you could, and maybe it's an unfair question, but if you could give us a sense of sort of the personal passions underlying this work that you've done, or the kind of satisfactions that you personally find in doing it. In other words, sort of what's in it for you doing all this work?
It was just so much fun. You know, I found I loved computer science. I loved programming. These problems were so interesting. It was clear they were really important. And it was just, I like understanding things. I like inventing things. You know, it was just like a perfect fit. And I was never thinking about awards or anything like that. I was just interested in the problems and finding out elegant solutions, and it was fun.
That sort of intellectual
Yeah.
challenge and satisfaction.
Absolutely.
Okay.
Yeah. It was really amazing.
And it must have been in a time of such growth and change in computing too, to be
Yeah.
at the center of that must have
Yeah,
been.
it was great.
Yeah.
Yeah.
The next question we had was if you could tell us a little bit about some sort of major challenge or some sort of dark moment in your career or your work and how you overcame it.
So I don't really feel like I had dark moments. There certainly were times when things may not have gone just exactly the way I wanted. Like, for example, when I got my Ph.D. at Stanford in 1968, it was, I would have liked to have had a faculty position, but I didn't have any decent offers. So that was, you know, a little disconcerting. But on the other hand, I was working in software. There was, you know, so much I could do. I took a job as a researcher. Turned out to be a really good thing to do because I was switching fields out of AI into software systems, and I didn't have to be distracted by teaching classes and doing all the other work that is associated with being a faculty member. So it was, in some sense, a setback. But on the other hand, it was actually sort of a gift. And I think many people's careers are like that. You know, something gets in your way, but something else happens, and you know, you find your way. I don't know. I mean, I never thought about stopping, or I never got really upset about it. I just sort of I was like that little engine,
Yeah,
the little engine
right,
that could,
that
yeah.
could.
Right.
Well, I read a quote from you in one of your previous interviews where you were talking about, I guess, another maybe surprise. I think when you were applying to graduate school, and you got a note back from one school that said, no one of your gender need apply.
Right.
But you had a quote in there was something like, your style was never to really give much attention to negative signals. And it seemed like that, you're just following the
Yeah.
work and...
Well, if you think about what it was like for women at the time, so I felt all through high school that there was a sense that I wasn't doing what I was supposed to be doing. I mean, I was interested in math and science. That wasn't really the thing.
Right.
I was interested in academics. Even that was not really the thing. And so I guess, I don't know where it came from, but yeah, I just kind of did what I wanted to do, and I didn't pay much attention to, what people thought about it. I was aware of what they thought about it, but I wasn't paying much attention to it.
Yeah, that kind of a kind of a self-determination, if you will.
Yeah, something
Yeah.
like that.
Yeah. In thinking about the areas in which you've been, very active in your work, programming methodology and programming languages, and distributed computing, what in those areas today in the world have most sort of surprised you, where they have arrived to in the contemporary moment?
Well, I think, like so many of us who were early researchers, the thing that really surprised me was when the internet took off. And so for all those years up to the early 90s, what we had the ARPANET, we had a community of researchers, there were certainly companies that were developing software, business software and stuff like that. But the public at large was totally unaffected by this. And then all of a sudden, and Tim Berners-Lee invented HTML, but probably also the hardware got to the point, you could by then have personal machines and stuff like that, and the whole thing changed. And really, it was a revolution, an information revolution akin to earlier revolutions like the Industrial Revolutions. It's made a huge effect, has a huge effect on what's happened to our lives. And I sure didn't see it coming. It was, I wasn't thinking about it. I'm not a science fiction kind of person, but it was just took me totally by surprise.
Even for someone who was so kind of at that point deep into distributed computing.
Yes, but it's a big change from that to a computer in everybody's home.
Yeah.
Yeah, it was distributed computing, sort of writ small, supporting software for businesses and software for the government, but not social media and all the stuff that came later. Yeah.
Thank you. What would you say is the biggest misunderstanding about the kind of work that you've been involved with? If there is one.
I don't know what people understand, so it's hard to answer that. So I don't know.
Yeah.
Did you have something in mind?
No, I really didn't. That was kind of an open-ended question.
Okay.
I guess one thing that interests me in common discussions is how much there's sort of a discussion about technology and software in particular as if it just creates itself, and there's not a lot of discussion about all of the people behind every development that occurs. There's and all of the labor that goes into creating.
Well, you
armed
did
world of software.
remind me of the way it used to be when computer science was sort of disregarded. People in both science and engineering sort of thought, there's no intellectual content here. We can build everything ourselves. We'll just, throw it together. And this was a thing for many years. And it was also true that many of the early computer science departments were founded by mathematicians, and they weren't very interested in the more engineering side of things. So those kinds of misconceptions definitely existed. And one of the things that Dijkstra was doing in his early work was he was trying to point out that actually computer programming is hard. Reasoning about the correctness of programs is hard. And he was trying to counteract some of that, I don't know what to call it.
Yeah.
I'm not sure that the scientists have gotten over it entirely even today, although you would think they would by now. Yes.
And also this interesting this interesting connection in that your work shows is in that this work in sort of the theoretical side of computer science can directly connect to the more engineering part of computer science, that there's such a strong coupling there.
Oh, yeah, absolutely. And I always had my students take as much theory as they could, and we always worried about how do you prove the correctness of your systems. And of course, when I start all the work I did in distributed systems makes use of cryptography and the contributions of theoretical computer science. So yeah, but this is how computer science is, everything is connected together.
Right.
Yeah.
Thank you. Another tough question to answer, kind of hard to ask, but the question is about legacy. If you're thinking about, which is not maybe something that people think about every day, but if you had to think about, what would you like the legacy of your work and your contributions to be, how would you think about that?
I have no
Yeah.
idea.
Yeah.
I did what I did, and I hope it's remembered. I do worry about where we're going from here. And this is something you probably do want to talk about at some point, what's going on with social media, where we're heading with AI. But, I was...
Would you like to talk about some of those concerns that you see moving forward now?
Well, I certainly didn't think about much about human behavior and what would be enabled by the presence of all the social media platforms. And I have been pretty appalled at what goes on, the fake news, the dissemination of bad information, the attacks spread faster than good stuff, all that sort of stuff.
Mm-hmm.
I think, but of course, if you look back at history, so here we are in a kind of a politically fraught time. But if you look back to the 50s, we had Father Coughlin, we had McCarthy. Long before we had social media, we already had Fox News. We had, now we have these podcasts that are, and talk radio. So it's not like we're the only perpetrators. In fact, it's not even clear that what's going on online is the major problem, because I think maybe TV and radio is more the major problem. But still, it worries me. And I think that it's really important to the extent possible to provide technological solutions that avoid propagating misinformation. I think we could be doing more of that. And of course, as you know, there have been problems with some of the work that's been done, like, for example, hiring people based on past history and pretending, or were they pretending, or did they were they really taken by surprise that all the biases that
Right.
had previously existed went right into the machine learning problem? I don't know why I ran off on that. So, I worry more about what's going to be happening in the future. What I did was I made contributions at a particular moment in time when there were important problems to be solved. And then, things have moved forward since then. I decided not to work in AI, but I know that friends of mine who did work in AI, they were probably even more surprised than I was at where they thought they had a vision of how wonderful it was going to be and turned out to not be. I mean, mind you, things have been wonderful. It's just that there are also problems.
Right.
Yeah.
Right. Well, thank you. Well, maybe this is a question directly in that vein. As you consider the challenges facing people and our planet, what new technological innovations are you the most optimistic about making, a difference?
Well, there I think you've got me. I'm not active in research anymore. Certainly, you can see good applications coming along. There have already been great advances in robots helping in medicine and AI helping in medicine. I think that, properly done, we can continue to make progress there. Certainly, robots can be very helpful when used in the right way. I can see all the good uses. And I guess that's what you were asking me about. No, I can really see and you know what I wish? I wish there were robots that could take care of recycling. I think part of the problem with recycling is we have all these different things that have to go into different bins. It's tedious, but it seems really something that robots and AI could manage pretty well, and that would be very helpful. So,
Yeah, great. I guess the next question I want to ask is, reflecting on becoming a fellow of the Computer History Museum and joining the other kind of trailblazers in computing who are fellows of the museum, what does that mean for you? How do you react to becoming a fellow of the Computer History Museum?
It's very nice. I feel that one of the things that was really lucky for me was that I got into the field early, and I actually knew a lot of these people personally, going right back, to the beginning. So they were friends, or at least acquaintances, and it's a nice community. So I'm very happy to be a member of it.
And the last of these general questions is, drawing on your wealth of life experience, what one word of advice would you give to a young person, starting out in life or their career? Is there one word of advice you could give? If you had to give just one word of advice, what would it be and why?
I can't give one word of advice, but I think that if you're going to be successful, you need to pay attention to what you enjoy and what you're good at. And you also have to think about what's going on around you and what's important and what's not. And it's hard to sometimes sort all that stuff out when you're young because you're finding yourself. But that's what I talk to my students about.
Is that sort of attention to themselves and the context?
Yeah, you know, people come into college, they have ideas of what they're going to do. They have to learn what the right way to go is. And then the whole experience of my jobs with, you know, doors closing and doors opening. And I think this is what careers are often like. And you just have to sort of figure out what the right path for you is. And it's very important to do it ethically.
Yeah.
Right.
Yeah.
Yeah.
That's a great piece of advice
Yeah,
for
right.
sure. Well, great. Well, thank you for starting with those. I know those general ones are not the easiest questions to start off with. Oh yeah, you know.
I'm now having a drink. I
course.
figure we're having a few minutes.
Transition moment. Yeah, thanks.
Yeah.
Well, oh sure.
Oh, you've got more Kleenex there. This is lovely. Yes. Thank you. Yeah. Yes, if I do need to take a drink of water or something, you'll sort of.
Yeah, we'll cut that bit out.
Yeah. Okay. Thank you.
Of course. Well, now just to kind of switch gears to more of a biographical mode, if you
Okay.
will. I understand that you were born in California
Yes.
in 1939 and that you grew up in San Francisco.
Yes.
Could you tell us a little bit about your family of origin and your parents?
So my father was a lawyer. He went to Harvard and then to Harvard Law, and he was one of Felix Frankfurter's little hot dogs. Frankfurter was a professor at Harvard Law when my father attended, and his little hot dogs were people that he placed in the Justice Department.
Oh.
My father worked in, when he met my mother in San Francisco in, I think, 1937 or something like that. He was in California because he was prosecuting Standard Oil for antitrust.
Wow.
So, and my mother grew up in San Francisco. Her family, her mother was born in San Francisco. Her father was born in Texas. So they had a long history in San Francisco, which is, you know, San Francisco isn't that old.
Right.
Yeah. So this is, she went to Berkeley, but then the Depression hit after she graduated from college, and her father was a pharmacist, and they didn't need money, so she was working at a daycare center, but she left because those jobs were needed by other people.
Oh, yeah.
Yeah, but she was, she never worked after that. You know, she met my father, she devoted her life to that. It was that particular kind of middle class, you know, way of living.
Right.
Yeah.
And did your father spend his career mostly in the Justice Department?
No, he left the Justice Department in 1943, maybe. And I understand from looking at a book about Frankfurter that he was not happy about some stuff that was going on in the Justice Department. But my mother probably was also really pushing him to move back to San Francisco.
Oh.
And anyway, so we moved to San Francisco. We opened a private practice, and that was around 1944. So that was where I grew. Before that, we were living in Alexandria, and I was actually born in Los Angeles
Oh. Huh.
because he was prosecuting Standard Oil.
In
Yeah,
Los
right.
Angeles. Okay.
Yeah, right.
You know, oftentimes when we interview people, there is like a prominent theme of the household, the household of your youth. For some
Yeah.
people, it's like music. For some people, it's business or religion or politics, technology. Are there any strong themes that stand out for you, for your household?
You know, I don't think so. And I've thought about that because I certainly have seen interviews with people that talk about, you know, my father used to take me out and we'd talk about this and that. This kind of stuff was not really happening for us. There were 4 of us, so a fairly large family. My father went to work every day. You know, my mother was quite social, and there was nothing. It was not like I was being pushed in any particular direction. The only thing was we were supposed to do well in school, and it was expected that we'd go to college. But
Okay.
you know, but there was no discussion about technical stuff or other than, you know, here are your grades.
But there was that kind of implicit emphasis on education.
Oh, absolutely.
Yeah.
Yeah, absolutely.
Was reading a big thing for you as a
Oh,
youth?
yeah, I was a reader.
Could you talk about what sorts of things you were gravitating toward?
I read it was fiction. I
Fiction.
wasn't reading technical stuff. I don't think I was reading history. I think I was just taking books out of the library at random and reading everything I could get my hands on. My mother used to force me to go outside and play.
Okay. Because one of the questions I always ask people is about, you know, if the library was a big part of their youth, and it
Yeah.
sounds like for you it
Oh,
really
yeah,
was.
absolutely. Yeah.
Could you tell us a little bit about your education up through high school? Was it in, where did you go to school?
Public school in San Francisco. I mean, it was, you know, there was elementary school, there was junior high. And then I went to Washington High, which is in San Francisco, there's an exam school, Lowell.
Okay.
Though I'm not sure it was an exam school at the time. But Washington, which was within walking distance of my house, and so there was never any idea that we would, you know, go to Lowell, which I guess was maybe better regarded. It was a perfectly.
And was it for you in high school where you really thought, wow, mathematics and I guess science too were things that
Yeah,
those were your things?
I was just really interested in them.
Yeah.
And I could also feel that maybe that wasn't really what I was supposed to be interested in. But and at Washington, in my senior year, I was able to take pre-calculus. So that sort of gives you an idea of what was going on in those public schools at that point in time. That was a very small class. I don't remember how many, but, you know, maybe 10 people, something like that.
Right.
Because my recollection is that in my high school there were maybe 10% of the kids were interested in going on to college. It was really different then than it is now. And maybe we've gone too far in the other direction since, you know, there are very good trades and stuff like that that people can spend their lives in.
Absolutely.
Anyway, so...
And so it had been an expectation in your household that you were going to go to college. And was it also was from your mother's experience having gone to Berkeley? Was kind of Berkeley especially on your radar?
Oh yeah, absolutely. I would think Berkeley it was expected we'd go to Berkeley.
Okay.
I mean, why wouldn't we go to Berkeley? It's a great school. It was free.
Yeah,
right. And there were no travel costs. So yeah, I decided I wanted to go to Wellesley. I'm not sure where this came from. And my father said the only school he would be willing to consider was Radcliffe.
Did you take a look?
I had for some reason, I was very negative on Radcliffe. I mean, none of this is based on any sort of fact.
Right. Yeah.
But so there was sort of, you know, Berkeley was the place to go.
And you were at Berkeley from 57 to 61, is
Right.
that correct?
Yeah.
Could you, and those are sort of like the immediate post-Sputnik years, you know, did that dynamic feed into anything that you were experiencing in
No.
math or science?
But here's a funny story. My husband went to MIT. He's a year older than me, so he started MIT in '56. And at some point, he was on a bus, and the bus driver said to him, "So what are you guys going to do about this?" You know? Yeah.
And he went on to work in satellites, did he not?
He was a communications engineer,
Yeah.
electrical engineer, yeah.
So I guess he
Yeah, right,
did
so he was doing
something.
something about it.
Yeah. Well, maybe then could you just describe a little bit about your experience at Berkeley, getting into, I know you started studying physics,
Yeah.
but could you just describe sort of the course of your
Well,
development?
I loved Berkeley. And I was definitely, I originally thought I would major in physics. After a while, I realized I didn't really have great intuition for physics. I was much better in math, so I ended up majoring in math. I took various languages and other, stuff, but it was mostly math and science that I was studying. But, college is a sense of freedom, and Berkeley was a wonderful place to be, and it was a beautiful campus.
You were living on the campus?
I started off living in a dorm. I hated it, and so I pledged a sorority because they had a dining room with windows, and it wasn't noisy. And I was in the sorority for a year and a half, and after that I lived in apartments. So my mother always lived in a boarding house, so I think, the dorm thing was, maybe the plan always was to end up living not in a official,
Right.
right.
And with Berkeley being free in those years, was there a necessity for you to work during your college years?
No. And there was a fee, and of course you had to have your living expenses and so
Right.
forth. I mean, I felt if I'd had to work, I could have managed. It seemed that, I did actually end up working every summer, but I was a counselor at a summer camp. My uncle actually ran a camp in New Hampshire, and I worked as a counselor there a couple of years.
Oh.
I worked as a secretary at the Jason Summer Study Group, which was a physics project being run at Lawrence Berkeley Labs.
Oh, yeah, with kind of a
Wheeler was
high-powered
there,
thing.
and yeah.
Right?
Yeah,
Yeah.
but I was a secretary.
Well,
Yeah. And I worked one summer as a counselor at the San Francisco Boys Opera Chorus Camp because my brother was in that. He was in the chorus.
oh, wow.
Yeah. So, I was working, but I wasn't working in a way that was going to earn me a ton of money.
Right.
Unlike my husband, who worked as an electrician, he came from a much poorer family and really had to. And MIT was not free.
Right.
Yeah.
Right. Did you have time for any kind of activities outside of the classroom in those years?
Oh, yeah. I got into folk dancing, and then I had a boyfriend who introduced me to hiking. And the first time I went to Yosemite, so, and then I found the high country, which is so wonderful.
Right.
Yeah. And so I did a lot of that. Yeah. Berkeley is not a place where you only study.
yeah, thank goodness.
Yeah, right.
Well, as your Berkeley period was coming to an end, what were your thoughts about, what you might do with your career or your life? What were your thoughts like at that time?
Well, so I thought I might go to graduate school in math, and I applied to Princeton and Berkeley. And I got into Berkeley, but Princeton is the one that sent me the postcard saying we do not admit women. And I was really surprised by that because I knew they didn't admit women to their undergraduate program, but I somehow thought it was different at the graduate level. That's okay. I mean, I really didn't care because Berkeley would have been just fine, but then I decided I'm not really ready to go to graduate school. And I was curious about Boston because my father's family came from New England. And I had a friend who had gone to Stanford who was interested in going to Boston too, so we decided to move to Boston. And I arrived in Boston, started looking for a job. And my aunt, I was staying with my aunt, my father's sister, and she said, oh, you know, I don't know, she had some idea about you're only going to be able to earn a little bit of money. I mean,
Yeah.
and I guess, you know, she was thinking I could be a secretary, because that's kind of what was open to women. But
Sure.
I was able to find a job as a programmer.
How did you find that?
Just looking at, you know, in those days there were ads in the newspapers.
Yes, yeah, as simple as that.
Yeah, and so I didn't have any sort of person that was helping me. I was just applying to jobs. And I actually had two job offers. The other one was more of a math job. It seemed really boring. Seemed to be drawing graphs and stuff like that. You know.
Okay.
Whereas the programming, and I knew nothing about computers. I didn't even know they existed. But
What about it? Did it just seem like something that you could bring mathematics to bear on? Was there something in the
it just seemed
description?
intriguing.
Yeah.
And so I said yes.
And that was at Mitre.
That was at Mitre, yes.
And this is 1961 or
Right,
so?
yeah.
So Mitre is a very young place at that time, right? I mean, it was only created
It was
in
young. I mean, I don't remember how
58
young.
or something.
Could be,
I think,
yeah.
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 And was it in Bedford?
It was in Bedford.
Okay.
I was living in Cambridge. So I had to buy a car. I bought a '53 Chevy. It costs, I don't remember. I remember $50 or $100. I mean, used cars were very cheap in those days because people wanted new cars all the
Okay.
time. This was the sort of the way that the car companies had manipulated things. But anyway, so I had to buy a car so I could commute. But I mean, it was great. That was a great job.
What part of Mitre were you working with? Was this on, because were they still working on Sage at that time, the Sage system, or?
I don't think so. I went to see Sage at Lincoln Labs. I saw the huge room with all the vacuum tubes.
Right.
But no, we were using, it could have been a 7090.
Okay.
Maybe. But I mean, the fact that I was just a programmer. So,
Right.
you know, whatever this stuff was in aid of, it wasn't my problem. I was just, you know, asked to build particular things. And
I guess they were doing air traffic control sort of things then. Might it have been for that?
yeah, but what I'm saying is that it would have been, you know, I don't remember any of the stuff I built, but it would not have been, here's the technical problem, figure out what to do about it. It would have been, here, we need this, you know, program to do thus, and so, sort of pre-specified.
Right. Right. And it
Yeah.
would be more maybe on the farther away from the application, if you will.
Yeah.
And more about the kind of compute part of it.
Yeah, I think
Okay.
so, right.
Okay.
You know, so how do you run the tape drives in order to make this work well, that kind of stuff.
I understand.
Yeah.
Could you describe a little bit about sort of the preparation you were given to, or the lack of preparation you were given to begin programming?
There was no preparation. They just handed me a Fortran manual and gave me a little problem to solve. That was it.
Okay.
So entirely self-taught. But I think that it was probably true for everybody that was working there. I mean, they all came in, they mostly had no knowledge about computers because there was no undergraduate program. And they were coming in with different backgrounds. I mean, I think some of them were from English majors. You know, it had more to do with could they think logically? Mm-hmm. I'm not sure how they figured out who they were hiring. A fair number of them were women. And you could either do it or you couldn't. And you either liked it or you didn't.
Right.
Yeah.
And let me just take a glance at my question list. Oh, so did this require you didn't have to have a security clearance or anything
No,
like that at that time? One person who I was lucky enough to do an interview with a couple years ago was Judy Clapp, who also
so
worked.
Judy was my boss, not then, but when I came back after graduate school, which we'll get to later. And I still am in touch with Judy.
Okay,
Yeah.
great, yeah.
Yeah.
That's such an impressive
Yeah.
person. But so you hadn't encountered her in that first stint?
I'm not even sure that she was there yet, because she worked for Lincoln Labs before she moved to Mitre.
Right.
So I don't know.
Yeah. Yeah, I thought maybe she went with Mitre when it was created, but I'm not sure.
I'm
about
not
that.
sure, yeah.
While you were working at Mitre, did you have was there any sort of occasion to meet any of the other people working in computing or programming in the area? You know, there was some, but just wondered if there was any way for.
Well, you know, I
these
was
people
working
to
with
meet
a
one
group
another.
of people who at Mitre
Right.
who were doing programming.
Right.
I never met anybody outside of there, but you have to understand that I wasn't a professional yet. I was just a programmer. I wasn't thinking about a career. I was just
Right.
doing something interesting.
Right.
And you haven't talked about, you know, what programming was like in those days, but those were the
Please.
days of punch cards and batch jobs, you know, so you would put in your program and maybe 24 hours later or 48 hours later you'd finally get it back. Which is an interesting discipline. You have to really figure out what experiment you're running with this particular run, and you better have several things going, because what are you doing otherwise while you're waiting in the 24 or 48 hours for the stuff to go back? And then, of course, there were the printouts. You know, you would think about the size of a program in terms of the paper. Yeah.
Inches of.
Yeah,
program.
inches of paper. Yeah. Yeah.
But it seems like it was something that you really took to.
I really took to. Yeah, it was just, for me, it was interesting. I was good at it. I found an error in the compiler.
Oh, wow.
Well, you know, my program wasn't working. And I decided it was probably not my program, it was the compiler. They didn't want to believe me, but it actually was the compiler.
Oh, my God.
Yeah. Well, you know, compilers are complicated programs.
Sure, but I'm sure once you could identify that, you thought, okay, I really have some good ground in what I'm doing.
I don't know. You know, I was a kid.
Yeah.
Yeah. And, yeah.
Well, what made you, I think you were there for about a year, and then you changed jobs to work at Harvard.
I worked at Harvard, and I made the change mainly because I didn't have to commute. I was living close to Harvard, so that was much easier. But that turned out to be a good switch professionally, because I was working in Fortran at Mitre. At Harvard, I was working in assembler.
Oh, wow.
And so when you work in assembler, you see what the machine is doing.
Right.
And so when I was at Mitre, I saw the machine through Fortran, and I didn't really understand the details of what the compiler was doing. But once you start to see the machine language, you have a much better understanding of what's going on with the compiler. And also, I was maintaining a big program written in assembler, which means I was looking at other people's code, which makes you much more sensitive about what's good code and bad code, since whatever they did wrong is going to come up and bite you.
Right.
And so maybe, you know, some of the stuff I did later in program methodology actually was already starting then, because I was already starting to think about what's good and what's bad.
Were you, in terms of what was bad or difficult to deal with, some people I've talked to have described, you know, some of the programmers of this period doing tricky programming, you know, where you were doing things that were kind of low-level tricks to squeeze some performance here and there out of things.
Non-reentrant code, where the program would modify itself to make things a little faster and then maybe forget to modify itself back. But this was pretty clean code.
Okay.
I think it was a pretty well-written program. It was a program to do machine translation, and they were hugely optimistic about how easy this was going to be. Although at the time they couldn't actually parse English sentences. So
Were they working on Russian to English, or?
I probably wouldn't have been Russian, but you know, they hadn't gotten that far yet because yeah, right. And but I mean, again, I was a programmer, so I wasn't doing the research. I was just, you know, they would describe to me something they needed to have changed in the code that was there, and then I would figure out how to change it. Or they would describe a place where they had found an error, and then I would figure out how to sort it out. But this process of having to look at a great big program written by other people, it does impress upon you the importance of a well-organized program.
Was this also your first connection into the world of artificial intelligence?
You know, I really wasn't doing any technical work in AI. When I look back on it, I think that when I got into Stanford, they expected me to work in AI because of this experience at Harvard.
Okay.
But I had no expectation of which area in computer science I was going to be going into. I had any real conception of what was there.
Right, right. Well, could you tell us a little bit about that decision to go to graduate school? I think that was in 1963 or something?
I started at Stanford in 1963. And yeah, so I must have applied in the fall of 1962. And I think I just realized that I liked it. And if I wanted to go further, I needed some education. So going to graduate school seemed like a good idea.
Okay.
And, you know, I had thought about getting a Ph.D. earlier in math. Now I was thinking about computer science.
Okay.
Yeah.
And what, there weren't a lot of options at the time of places to do this kind of work. Is
So
that
I
true?
applied to Stanford and Harvard. Berkeley didn't have anything. Stanford only had a program. And I forget what they had at Harvard, but they had something going on. And it was Aiken was the guy who started up the lab there.
Sure.
And I decided to go back to Stanford because I thought it was time to go back home again. Yeah. And, you know, so these decisions you see being made for sort of odd reasons, like...
Well, that's it. I mean, that seems like a very real reason.
Yeah.
You know,
But they're not, you know, like, this is the best place for me to get the...
Right. Yeah. It's a human reason.
Yeah.
Well, you were at Stanford from 1963 to 1968.
Right. Yeah.
An interesting time in American history. I was just wondering, before we dig into your, you know, your development in the world of computing happened in those years, you know, I just wondered, you know, being at Stanford at that time, what was happening for you around these big developments, like around the Vietnam War and civil rights and women's rights and this whole sort of world. I wonder-
Okay.
Oh, yeah. Yeah, of course.
So, yeah, hang on. So John Kennedy was assassinated in 1963. I remember being in a class at Stanford and the professor told us that this had happened. I remember the Cuba crisis, but that was before I went to Stanford. That was when I'm pretty sure that was when I was living in Cambridge. The free speech movement started at Berkeley. I felt kind of sad that I wasn't involved in it. Berkeley was like a hotbed of stuff happening. Stanford was much calmer. In fact, I actually thought it was kind of boring compared to Berkeley. It was very different than it is now. But Berkeley has always been kind of a hotbed of stuff. The problem with Vietnam was much more serious for the boys. You know, they had to worry about, am I going to be drafted? How am I going to manage that? I sort of put my head down and just, focused on studies.
Right.
Yeah.
Well, could you tell us a little bit about, what your experience was like in those years at Stanford? I know you worked on chess endgames in the context of artificial intelligence.
Right.
Maybe you could tell us a little bit about how you came to that as the focus of what you were going to work on.
Well, I was a research assistant for John McCarthy.
Okay.
And my recollection is that I met him walking up the stairs my first day there, and I asked if he could support me, but that probably is not true. But it's quite possible that he expected me to work with him because of the AI stuff that had been going on. Anyway, I worked with John, so of course I was going to be doing stuff. Actually, it's not of course, because John was very broad, and he did a lot of stuff on reasoning about programs and so forth. He was doing stuff that maybe was more the kind of stuff I turned out to be interested in, but for some reason I wasn't doing that. I was, in sort of AI. And he suggested chess endgames as a thesis topic. He liked the fact that I didn't play chess because he thought that way I would approach it as a computer scientist rather than a chess player. Read the book, figure out what the algorithm is, which is in fact exactly how I did it. And chess was a challenging program in those days because computers were small and slow, and you needed to do search, and you couldn't do very big search, so you had to have very clever heuristics and ways of pruning the tree. And endgames were considered to be quite challenging, and they were sort of a separate problem from a lot of the other parts of chess. So I worked on that for my thesis. Stanford was really good. I had great courses. I learned a lot about a broad range of topics. Nicholas Viert was there. He came maybe in my second year. John Reynolds was there. George Forsyth was the head of the department.
Right.
I knew all these people. They didn't have theory yet. Don Knuth showed up, I think, my last year there, but their idea of theory was mostly numerical analysis, which I hated. But they had programming languages. They didn't have much in systems. Compilers were sort of a thing in those days. That was a topic people were really pushing on. And so it wasn't programming languages, it was compilers and how they were organized, and numerical analysis. And I took a lot of courses with Dana Scott, so that was logic, and
Who was new to the
he was
campus
not
then,
he was in the philosophy department.
Okay.
And he was talking to John, and I got to know him, and so I took these courses that he was offering. I just was, I learned a lot. And
Had Ed Feigenbaum arrived?
Ed was there. I'm not sure when he arrived, but yeah,
After you, I think.
after I came, I
Yeah,
think.
yeah.
But he was definitely there. So this sort of a who's who of what,
Yeah.
yeah.
And what about your kind of cohort? Of graduate students at the time?
Well, I think there was a very small Raj Reddy. I think Raj showed up the year I showed up, but maybe he came a little bit earlier, but I always thought of him as, so there were 5 of us who took the first qualifying exam. And Raj and I passed, and so did, maybe there were 5 of us who passed out of the small group who took it, something like that. And that was maybe in my 3rd year. So that's how new it was. We weren't, it was just a program, and that was the first time the quals had been given.
Right. Wow.
Yeah.
Well, what do you think were some of the most important experiences for you personally that you had at Stanford that kind of shaped what you did afterward?
Well, I actually think just learning about all this stuff was good. And the fact that I had to build a large program all by myself, where I started from first principles and did the whole thing, that was something I hadn't been doing before.
Mm-hmm.
But I was also discovering that I didn't want to be an AI. And it was mostly because I was interested in machine learning and the way machine learning was done in those days, which was to try and make it sort of logical the way people think. I felt it was just too hard. It wasn't, working.
Mm.
And I was really interested in the compiler course and the stuff that was more over in the software systems area. But I made a conscious decision not to act on that. Nicholas Wirth invited me to come and work with him instead, but I decided to stick with John because I thought I'd finish faster that way.
Mm-hmm. Mm-hmm.
And I'm sure that was true.
Yeah.
Yeah. So I began to see the sort of the breadth of computer science, and I began to see where the direction I looked interesting to me.
Mm.
And I was learning everything that anybody knew at that time,
Right.
because it was a long time ago, and there was a lot to learn. Yeah.
I just wondered, thinking about machine learning, were you exposed at all to the work that Bernie Woodrow was doing at that time?
I recognize the name, but I can't remember what he did.
Yeah, he was doing more kind of like a hardware approach to machine learning. It was more like an electrical engineering approach, creating these sort of, I'm going to get it wrong if I characterize it, but it was an adaptive system, maybe you would call it, they were called Adeline and Madeline, these systems.
Yeah, no, I
and-
didn't know
yeah.
these systems at
Yeah,
all.
it was in a different kind of corner.
Yeah, I was aware of something called the advice taker.
Mm-hmm.
I was aware of general problem solver.
Right.
This was sort of the sort of the way that people were thinking about AI at that time.
Right.
And I was not aware of the work on neural networks, which maybe had already started.
Yeah.
But as I'm sure you're aware, there was this sort of schism in AI.
Yes.
And the work in neural networks was considered by the mainstream AI people to not be the thing.
Yeah.
But I got out of AI, and so I, avoided this whole controversy. Yeah, right.
Well, as you're finishing your thesis, could you talk about how you were developing, what was going to be your next step?
I was being very naive. I really didn't. I didn't think, I knew nothing about how to apply for a job. But the times were very different then too. And I think that a lot of the jobs did come in through the Old Boys Network, and it wasn't the way it is today.
Right.
But at any rate, I just knew that I was going to go on in the field. And as I said earlier, I would have liked a job as a faculty member. I did have an offer from one of the state colleges in California, but I smartly decided not to do that.
Because it would have been so much teaching.
Yeah.
Yeah.
Yeah. And I also had an offer at MIT to join the Multics project, but I cleverly said no to that too. I think that was important because when I went to Mitre, I went back to Mitre as a researcher. This is when I worked for Judy.
Right.
And at Mitre, I was handed projects that I could run. At Multics, if I'd been there, I just would have been, a member of the staff. I would never have been able, I don't think, to develop into an independent. I mean, I have no idea since I didn't do it, but I felt that being able to run my own projects at Mitre gave me a leg up, allowed me to find directions that I would never have been able to do as just a member of a team.
That makes sense. Well, because Multics at that stage, I mean, they were really pushing to try and
Yeah. I mean, I would have
produce it,
learned, who knows what would have
Yeah,
happened.
yeah.
But it seemed to me, I felt that in the end it worked very well for me to go to Mitre.
kind of more open projects to steer them in a way.
Yeah,
that
right.
yeah.
Here's your, the thing you're going to be in charge of.
Right.
Yeah.
Well, so could you talk a little bit about that, the kind of the job that you got at Mitre, and what sort of section of the organization were you in, and what was going on?
Okay, so again, I was not doing defense work per se. So I was doing research projects that were of interest to the Department of Defense. And I was not at the level, I was not required to go out and look for these things myself. So
Okay.
somebody else was finding them and handing them off to me. So the first project that I was given when I arrived, and I must have had an agreement with them, though I don't remember this, that I was going to be working in systems and not in AI. Because the first project I was given was to evaluate the value of what was called microprogramming.
Mm-hmm.
So this was when you had a read-only memory and a very small instruction set, and from this you could build a more sophisticated instruction set. It was almost like you took the lowest level of a system and stuffed it into the hardware.
Right.
Yeah, and so that was the first project. I mean, this was a very interesting project for me because there I was down at the sort of computer architecture level and having to design an instruction set. I met with Dijkstra during this period, and I got very interested in semaphores. Those were the early way that you did critical sections with the P and the V, which are just wait and signal.
Mm-hmm.
But Dijkstra was this original paper on the THE system that sort of laid this all out. And so I put those into the hardware. And then we must have built an assembler, although I don't remember doing this, because the next step was to then make use of this instruction set. And
Right.
we built a little timesharing system. And timesharing was still a sort of an interesting thing at the time. I mean, actually, operating systems continue to be interesting for years and years.
Sure.
But it was sort of early days then. And that was when, so that was sort of like the second year that I was there. We built this time-sharing system on top of the instruction set.
Okay.
And that
Okay.
was the first project. And by the way, I had to give talks about it, which I had not done before. So this was also, a useful experience.
Of course.
And yeah.
So the idea behind the kind of motivation behind microprogramming at this time was the idea of sort of the right machine for the job. You
Yeah.
know, you can customize the instruction set to have the kind of computer to do whatever it is you want to do.
I
Is
don't
that-
think it was a terribly successful research direction, was, my take on it. I mean, it probably had to do with let's not make the hardware very complicated, and then we can add the second layer and get something more sophisticated.
Right.
But honestly, you could have built that layer in software. Why it, really mattered that it was in this microprogramming layer. I haven't thought about this for years, and then I was thinking about this a couple of years ago. Why was this interesting? I'm not sure, but that first project, we did successfully come up with an instruction set, which really did provide sort of the next layer up. And then we built on top of this. But in the end, I was never convinced that we couldn't have done the same thing in, software. Yeah.
And then you use that microprogrammed system to then build Venus, is that?
Yeah, Venus was
Okay.
the name of
The
that system.
time-sharing system.
Yeah, time-sharing system. And because I'd put semaphores in and sort of early low-level process management, I did have the low-level stuff that I needed to build a time-sharing system. So it sort of made, but I had to figure out that Venus was the thing. The fact that it was going to be a time-sharing system was not preordained.
Right.
So I had to come up with the idea that it would be a time-sharing system. And, yeah.
Because that was the direction that everything was.
It seemed
moving
like
at
a sense.
this
It was
time.
it was an interesting project at the time, and it took advantage of the stuff that had been built into the using the microprogramming. Yeah.
And was in building this time-sharing system, Venus, it seemed like your motivation was less about this is going to be, sort of the next greatest time-sharing system, but it was more about, well, to build this time-sharing system, I'm going to use these new approaches, right? Microprogramming, and then the other one being levels of abstraction.
Well, yes. So I guess I maybe was already starting to think about how you organize software.
Mm-hmm.
And I had read Dijkstra's paper on the THE operating system, which used this notion of levels of abstraction.
Okay.
And honestly, what I was building there were abstract data types, but of course I didn't really know that. I was building a device controller. I was building a file system, so I was organizing. I had to organize the whole thing, and I had to think about it. And I was starting to think about things in this way without really knowing that this was going to be a direction for my future work.
Mm-hmm. Mm-hmm. Well, I wanted to talk about one question
yeah.
that. Oh, I'm sorry. Yeah, take my fumbling around
Yeah.
for the next question as occasion for a drink. Here's just a personal question that I had
Yeah.
when I was kind of doing the preparation. Do you think it's right to think of levels of abstraction as a kind of modularity?
So I stopped, I'm not sure that levels of abstraction were actually defined.
Okay.
There was a time when people liked to think that you built from the bottom up and each layer completely obscured what was below it.
Yeah.
And so you had a sort of a strictly hierarchical sort of organization. And I don't believe you build stuff like that, but that was a sort of an idea at the time. Certainly the idea that you abstract from all the details of how things work and come up with something higher level that, we understand today is a service with an interface, that was very valuable. Now, exactly what levels of abstraction were, I'm not so sure.
Okay.
Yeah.
Well, in this time period when you're back at Mitre and doing this research, let's say from 68 into the 72 or something
Yeah,
like
I went to
this.
MIT in 72, yeah.
In this time period, it seems like there's a really active, or it seems in retrospect like there was this very active conversation going around amongst software people about this notion of a software crisis,
Yes.
and also these discussions about creating software engineering. You know, these NATO conferences and
Right,
people
yeah.
talking about modularity and
Mm-hmm.
how did this play into your world?
So
This
what
kind of
happened was,
conversation?
after I finished the Venus project, I was handed the next project. And the next project was to think about the software crisis and what could be done about it. So it was handed to me on a platter. And, you know, and it was a fascinating problem and obviously a very important problem. So that got me into this field of program methodology. And if you look back at Venus, actually there were two things going on there. There was, first of all, the fact that I had been thinking about this organization in terms of these abstractions, but I had also invented a modularity technique I discovered after, when I was reading all these papers about modularity and design and so forth, what I called partitions, because the way programs were built then, this is not how Lisp programs were built. So I was also very influenced by Lisp. But Fortran programs, Algol programs, there was often this big array of global variables, and then all the code interacted through the globals. And I decided that was a mess.
Mm-hmm.
And so I said, we're not going to do that. We're going to break the program up into these things I called partitions. Each module owned a piece of the global state and provided some operations that you could use to interact with it. So here you have abstract data types kind of sitting there.
Right.
But I didn't know they were there. But I introduced them to our team when we were building the Venus system. And as I read all these papers about modularity, I saw that I had this modularity mechanism that was more detailed and defined than what other people had been talking about. The rule about how the internal stuff was hidden inside and you couldn't get at it except through the interface, that was something that people hadn't quite pulled out yet. And so then this led me to write a paper while I was still working at Mitre about this idea of partitions.
So almost it sounds like your concept of abstract data types or data abstraction is kind of almost an abstraction from partitions. You know, to say partitions are an example of this bigger thing,
right.
Abstract data types.
The important distinction is that abstract data types come in from the top down because they talk about what is it this thing is providing. It has all the rules, but it also now has this additional piece that is, this is what it's doing. It is a data abstraction. It is providing objects with operations and so it was just putting, I mean, it's almost like you just see this series of happy accidents. You know, in Venus, I was interested in levels of abstraction. I organized the system so that it had these things that were like what we think of data abstractions today. I also came up with this rule about partitions, and partitions you can see now as classes, you know.
Okay.
All just while I was building the system. And then I was asked to think about the software crisis, and I saw the work on modularity and how do you reason about programs and so forth. And then I just had this stuff I'd already done that fit right into it. I was very lucky.
Yeah.
Yeah.
That's really incredible. So I was reading somewhere where you were talking about as you were reading this literature about modularity, the software crisis, all of this, as you were reading that literature, you saw that when people would be talking about modularity in software, they would also then like bring up data types.
They would bring up, so they didn't really bring up data types.
Okay.
They just talked about how you divide things into modules. And they would give examples of what these modules were. But the step of seeing them as data types hadn't quite happened yet.
Okay.
They did talk about modules as being groups of operations, but the fact that they were all, the operations all together made this thing that was a data abstraction, that sort of hadn't quite crystallized.
Okay. Okay.
Yeah.
Well, here's a kind of a, how would you explain sort of data types or types to sort of a novice, and explain kind of the place of types within computer science? Can you help elucidate that for somebody who's trying to, to really dig into this?
Oh, God, I don't know. Every programming language you use has some data types built in it.
Right.
And one of the funny things looking back is that there was work going on at this time. By the way, I'm already beyond Mitre at this point. I didn't really start working on abstract data types until after I left Mitre and went to MIT.
Okay.
So it was my first year in MIT when I sort of was able to make this jump from
Okay.
what was there to the abstract data types. People were working on what they called domain-specific languages.
Mm-hmm.
So the idea was you would design a new programming language with some special data types in it that were just right for this particular domain, whatever it was. So you can see there, but the thing that was holding people back was the idea that the data types had to be built into the programming language. And what happens with abstract data types is you say, no, it doesn't have to be built in the programming language. You can invent them yourself.
Right.
Just like you could invent procedures, you can invent data types.
Right.
And if you think about what's going on in a program, it's really all about procedures and data types. It's the machine has some data structures and some operations, and this is just the same thing. You're inventing an abstract machine. So that was what the innovation was, that now you didn't have to keep designing new programming languages all the time to get the data types. You just could do it straight out.
Right. And abstract data types was providing a particular kind of direction for people to create their own data types that had this advantage of this kind of encapsulation, this
Right.
modularity, this ability to, you can change out the inside of it and not affect
That's right.
everything that
Yeah.
depends on it.
Yeah.
So it's kind of a framework and approach for approaching.
That's right. And
types.
people were already doing this with procedures. It's just procedures don't take you very far.
Ah,
They just do a thing.
right.
But for a sort routine, you have what it does, and then inside you have how you do it. It's just they're kind of small, and data types are much bigger.
Ah.
A file system is a data type, a database is a data type. The big things.
Okay.
So you get much more powerful modules this way.
Okay,
Yeah.
thank you. Yeah. So let's, can we talk about then your, oh yeah, take a,
Your cameraman keeps telling me. Yeah.
reminding you whenever I'm fumbling, go for
Yeah,
the.
right. I should.
Do you have
that's right.
enough? Do you need the other?
No, I'm fine.
Okay,
Thank you.
Maybe we could talk about your recruitment to MIT then.
Yeah.
And before we get back into data types.
Yeah.
Yeah.
So what happened was, it's a cute little story. I should say, by the way, that it was only when I was at Mitre that I realized that I had a career. Prior to that, I'd been thinking, well, this is fun, but maybe one of these days I want to have a family and This was kind of how women thought about things in those days. But partway through my time at Mitre, I realized, no way am I going to stop, this very rewarding intellectual activity. But that was just by the way.
Yeah.
So what happened was I wrote a paper on Venus. It was a prize paper at SOSP, which is the top systems conference. And Title IX was about to pass. And Title IX was about athletics at universities, but what it really did was it opened up universities to women.
Right.
And it hadn't passed yet, but you could see it was going to. And certain universities were looking ahead, and MIT was one of them. Jerry Wiesner was the president. This kind of stuff comes from the top. And he was thinking that they should be hiring some women. And the department, it was the EE department in those days, they were thinking they should be hiring some women. So when I gave this talk at SOSP, there were people from MIT in the audience. The chair of my session was from MIT. Corbato was there in the audience. And as a result, I was asked to apply to MIT. So I applied. And I got the job.
When you say they were deciding to hire in some women to the faculty, was it that they decided we should hire in some more women to the faculty? Or
there were almost no women on the faculty.
Almost no women.
When I joined MIT, there were 10 women on the faculty out of a faculty of nearly 1,000.
Oh my God.
Yeah. And actually in those couple of years after I joined, a number of women who had been there as research associates became faculty members. So there were very distinguished women that were not allowed on the faculty. It's how it was.
Yeah.
Yeah.
Wow. So it really is almost bring people in for the first time.
Yeah, I mean, and I don't
since
think they hired very many in my year. In fact, when my husband and I went to the reception that they had for new faculty, and I was probably the only woman in that cohort, the chair of the corporation walked up to us and he says to my husband, he says, "Welcome to MIT."
No.
And
Yeah. So
yeah.
yeah.
It was early days. Yeah.
And what department did you join?
EE.
EE.
Yeah.
Okay. Yeah.
Yeah. It was before it turned into EECS, electrical engineering and computer science, but it wasn't EECS yet.
Okay. Now, so could you talk about once you got to MIT, how you decided to, take the work on abstract data types, you were kind of conceiving it. How did you come up with the idea of creating a programming language to further that research? What's the connection there?
Well, it was a necessary step. So what happened was I got to MIT. I was absolutely focused on this question of what is this modularity thing and how can we make it something that people can use? Because I felt that the papers had good ideas, but you just could not abstract from them the thing that would allow you to do your own design.
Yeah.
So each design kind of stood by itself. You'd say, that's great, but when you tried to do your own design, it didn't seem to be helping. And so I was just focused on this problem, and I came up with the idea of abstract data types, which I could see was the solution, since it was this big building block, and now you could focus on these big building blocks and come up with your design that way. But it was totally unclear if it was going to work. From the point of view of would we build efficient programs that were performed well enough, programs that were convenient to write. It was all unknown. And so I had to do that next step of coming up with a programming language to make the whole thing hang together so we could see how the whole thing was going to work. So it was sort of obvious.
Okay.
Yeah.
Okay.
Yeah.
And could you talk about Steve Ziles and how he figured into this, to the kind of gelling of this
Yeah.
effort around the programming language?
Yeah, sure. It's Steve Zillis.
Oh, I'm sorry.
That's okay. And after I came up with this idea of abstract data types, I discovered, I think, so Jack Dennis was a professor at MIT, and he was very helpful to me. He was a co-author on the first NSF proposal. I think I wrote about the programming language stuff. And he was kind of showing, he's like a mentor, although I never heard the word mentor and I didn't really realize what was going on. But I think Steve was Jack's student, and so Jack introduced me to Steve, and Steve had some similar ideas. He'd written a little paper about basically abstract data types, and he'd shown how you could build them using Lisp, I think. I mean, I need to go back and look at that paper, but you can build anything and anything if you put your mind to it. And so we started to work together, and what we were working on is, what would this programming language be like? What are abstract data types really? What are the rules? How do you support them? How would what would the language be like? So we started thinking about that together, and it took us just a few months to come up with a sort of a straw man proposal for what this programming language would have in it, because we were finished with that in the summer of 1973. And then, of course, the next step, which went on for several years, was to actually design and implement the programming language.
Right. And that took about 5 years, is that right?
I think it was about, something like that, before the whole project was finished. Yeah.
And could you talk about how you mentioned the NSF grant to support the work. You also got a DARPA contract.
Oh,
I think.
But the way DARPA worked in those days is the lab had a DARPA contract.
Oh.
And this
okay.
DARPA contract included pieces, so mine was just a piece of it.
Okay.
And I just had to write a couple of pages describing what I was doing as part of this.
Got it. It was
Much bigger.
supporting the whole
And it
computer
was
effort.
much easier to get funding in those days than it is now.
Yeah. Well, how did you go? And the language was called CLU?
CLU.
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 For cluster.
Cluster, which is what we had. It was like a class.
Okay.
Yeah.
And could you just talk about the project to build the language? Did you have professional staff working with you, or was it mostly students?
It was all students.
All students.
No professional staff at that point. I got 3 young students that joined my group in 1973, and they were they and me, the 4 of us, were the people who really put the whole thing together. We used to have weekly design meetings. The people who came, there was a much larger group. Steve used to come to these. Steve was working on abstract data type specifications for his Ph.D. thesis, and Jack Dennis came, and there were other people who came and participated, but the bulk of the work was being done by myself and these 3 students, and we would write design notes. We would be focused on a particular question about how should this particular piece of the system, the language, work, and then we'd work out proposals and write them up, and it was a very interesting process. We had meetings where we would then discuss all the details and try to troubleshoot what was going on. And then, of course, we had to implement it. Yeah, and the students did the implementation.
And this is just a question out of my own sheer ignorance.
Yeah.
Is there a way to kind of incrementally test the implementation? That is to say, you have some sort of skeleton of the language that you can work with and then add more things, or does it have to be kind of more fully fleshed out before you can try it?
What we did was we implemented using a programming language called MDL, Muddle, which was a Lisp derivative, a small piece of the language. And then we wrote the compiler in this, it was really clue, but a very limited kind of clue. So we bootstrapped in that way.
Right.
And yeah, the first piece didn't have much in it, just enough to get us going. And then we sort of moved along and put more and more stuff in.
Got it.
Yeah.
And what were the computing resources like that you needed for this work?
I'm trying to remember. I think we had Vaxes, and they looked like washing machines. And they were up on the 9th floor, which was where the computer equipment was, all in a row, like we were at a laundromat. And we even named them after laundry products, although I forget what the names were, but they were named after
Like
different,
Ajax or
yeah,
whatever.
that kind of
Yes,
stuff.
that-
Yeah, right. Yeah.
And this, you were in the building in Technology Square
Right.
then?
Yes.
Yeah,
Yeah.
which had like the Laboratory for Computer Science, and was IBM in there
IBM
too?
had a floor, I think, and I think the CIA was there somewhere.
Yeah, they had.
So we didn't have the whole building, but
the
we had.
AI people were in
They
there?
were on the 8th floor.
Okay.
I was on the 5th floor. The theory group was on the, I forget. Yeah, right. We had most of, I mean, even I think we were probably on all the floors. I don't think IBM had an entire floor. Steve worked for IBM,
Right.
and but he was also a student. Yeah.
It seems just like a very interesting setup with all those organizations sort of in there.
Yeah, I don't think we interacted much with the CIA, but we obviously had some interaction with IBM.
Yeah.
Yeah.
So while you were working to build Clue, was the same time period when out at Xerox PARC, there is this group, as we discussed before,
Yeah.
developing Smalltalk.
Right.
And I was just so intrigued by that, that simultaneity, that, these two groups, independent of each other, are coming up with these developments that would become so integral to what we know as object-oriented
Right.
programming. I wondered if just, do you have any thoughts about that simultaneity, or why that would have been going on?
So I was pretty unaware of what was going on the West Coast.
Yeah.
The country was bigger then. You didn't fly across the country then the way you do now.
Right.
And so Simula 67 was a programming language developed by Ole Johan Dahl and Nystrom. I forget his first name right now. But anyway, and it was influential. I mean, Steve and I looked at Simula 67. We decided not to base Clue on Simula 67 for what I think were sound technical reasons. But it had classes, and it had subclasses. And exactly why Alan Kay decided to build Smalltalk, I don't know. But I mean, have you talked to Alan Kay?
Yeah. I mean, he talks about all of these influences, and
Yeah.
Simula being one, but it's just so interesting. I mean, it's just so interesting to me. Maybe it's people reacting just to this idea of modularity and building software.
And we better
in
find a
more-
better way. We've got to
Yeah.
figure out a better way of making it more productive. So I think that's the motivation in both cases. We just went in different directions.
Yeah.
And And, by the way, as far as my work was concerned, there was also the work at Carnegie Mellon. Bill Wolfe and Mary Shaw were building a language called Alphard, which was also like Clue, more of a data abstraction language as opposed to the inheritance was not the big thing. It was more, let's think about the meaning of a type, and then we have an implementation, that you could change.
Right.
Yeah.
I also was reading somewhere that in this period, Jim Mitchell and maybe some other people at Park who were working on the Mesa language
Mesa,
were
right.
bringing some of your ideas about abstract data types into what they were doing with Mesa and then Cedar.
Yes. In fact, there used to be a group of people, all of them getting ARPA funding, and we would meet once or twice a year to talk about what was going on in programming languages. So that included the Mesa group and the Alphard group and us. And there were maybe only 10 of us who would go to these meetings, and we'd just talk about where we were going and what we were thinking about. And
Oh, that's so interesting.
Yeah.
Yeah. So it's a sort of an ARPA contractors meeting
yeah,
for.
but it was sort of programming languages pushing in this direction. It did not include the Alan Kay school. It was much more the data abstraction stuff.
Yeah. That's so interesting. Let's see. So once you had kind of, when we're getting to sort of 1978 and Clue is becoming more fully developed, how did Clue influence your thinking about, if abstract data types were really going to work the way that you were hoping that they would?
So at that point, I was convinced they were.
Right.
I mean, Clue was a fully developed product, and we had users, and they were building big systems, and they were happy. I thought about maybe trying to make it into a real language, because in those days, something coming out of academia didn't count. You had to have a company behind it and so forth. But I decided not to do that. And that's when I got into distributed computing. But I was convinced then. I mean, I think data abstraction was a thing. It was successful. We knew what was involved. It was clearly going forward.
Okay.
Yeah.
And would you say Clue was its widest use throughout the 80s was for research and for teaching? Is that a fair characterization?
I think that's fair.
Okay.
Yeah. It never got into here's a place in industry where we're building a product, because it wasn't supported.
Yeah. Right.
They wanted something, that IBM, a language that IBM was behind. They wanted a commercial organization behind what they were using. That was sort of the mindset in those days.
But it did spread to many places.
Many places
for
were
teaching and research.
using it. Yes.
Yeah. As we were talking earlier about these two things, data abstraction and inheritance, kind of coming together and forming this kind of idiom of object-oriented programming that has become so widespread in many of the most popular programming languages today. What do you think is the most important? What are the most important things about object-oriented programming? What does it afford to people that other approaches don't? Is it?
So, honestly, it's just the modularity thing, and the fact that you start off with a behavior that you want You write a specification, doesn't have to be formal, describes what it's supposed to do, and then you have a separation between that and the implementation, which can change later. And this gives you the basis of a program methodology where you can think about, I like to think about it as an abstract machine. I just invent a machine, and it has exactly the data types and the operations that I need to do whatever this huge thing is I'm working on. And, then you could actually write a program at that level, and you have little specifications for the stuff that sits below, and then you can pick up one of those pieces and do it again. So you can build very big programs this way, but they're organized modularly so you can think about them independently. And so it just gives you the basis of the way people want to build programs. The thing that came in from Smalltalk was the inheritance, which to me has never seemed all that interesting, but lots of people think it's very important, so that's fine. Yeah.
With this kind of modularity, like you just mentioned, one thing that it affords is sort of scale. You can make very big things.
Yeah.
Does it also afford things like flexibility, that it's kind of quicker to make something new using this methodology? Is it more maintainable?
Yeah.
Are these some of the other reasons that?
You can build prototypes. You can have some module that you provide a very stupid, not very efficient implementation, but it's enough to get you off the ground. Then you can re-implement it later. I always told my students to think about designing around the places where you think there's going to be change. So you put abstractions there so that this way, if you have to change your specification later, you're sort of more prepared to make those changes. So it also gives you a tool where you can think about how to make things flexible. And anyway, it's already flexible that you can rip out an implementation and stick another one in.
Right.
Yeah. So, yeah.
Well, maybe we could talk about this shift to distributed computing. And I understand that, I think I read somewhere that you described you were looking around for another big problem that that could keep up with abstract data types. Could you talk about how distributed computing looked like one of those big problems?
Well, as I've said in many of these talks, I read a paper written by Bob Kahn. I haven't been able to find this paper, so it must have been, so I remember reading it, but I don't remember which paper it was, in which he described his dream of distributed computing, where you had programs with pieces at different computers connected by a network. And at that point in time, people didn't know how to build them. And so it just looked like a great problem to work on. So I jumped into distributed computing, and the first project I did was a programming language. So I basically took Clue and I turned it into a program, a language that would have components at different computers and communicate through remote procedure calls, and that was the start of working in distributed computing.
That was called Argus, is
Argus,
that correct?
yes.
And that I thought was so interesting because it was kind of like expanding this modularity to the network almost, is what I was getting from reading it, with these new sorts of data types to handle the fact that the computing is happening across the network.
Right. Well, really, it was just data abstraction, and we had a special kind of object that was a major component of distributed computing. We called it a guardian. The reason we named it Argus was the guardian of the gods, and a guardian resided completely in a single node of the network, provided a bunch of operations, which could be called by other guardians. And so it was just an abstract data type, but it was special in that when you think about a distributed computation, the question you have to ask yourself is, at the end of running this computation that visits many nodes of the network, how do you make sure everything that you wanted to do happens, given that messages can be lost, computers can fail, so this was the sort of the thing that got added, was how do you understand and make sure that you run a computation that either completes completely or has no effect. You want it sort of an all or nothing. And we borrowed this work from databases. We took transactions out of the database community. These are computations that either completely happen or don't happen at all. And we put that into Argus as the sort of basic way that a computation ran. So
that's interesting. Is there some connection there between transactions and communications? Like, is there some natural affinity there?
Well, transactions have this notion that either everything that the transaction was supposed to accomplish is going to happen, or nothing is going to happen. And I just picked that up because that was what I wanted in these distributed computations. I wanted to make sure that even though I started a computation at this machine here, and then it went over to there, and something happened, but by the time I got finished with everything, maybe that computer had failed. So I needed to think about, how do you make sure the right thing happens if everything is up and running, or the right thing happens if something went wrong and you don't want a half-done computation. I picked that right out of databases. They were mostly thinking then of a single system, where you have a computation where somebody's thinking about something and he does this and then he does that and then he does this, and you want to make sure at the end that everything happens. But they were already beginning to think about databases in more than one place, so this notion of distribution was already something to think about.
Okay.
Yeah.
And the transactions were a way to sort of certifying along the way.
They had a protocol called two-phase commit,
Okay.
which is how you end a transaction by making sure that everybody agrees that things can happen. And that's the first step. And if everybody agrees, then in the second step, they all make sure that they really do happen. And this involves writing stuff to a backup device like a disk. And, there's a protocol there.
And what was in that kind of motivating dream of Kahn's or whatever about distributed computing at the time, in the at the end of the 1970s, what was the advantage of distributed computing? What was it offering that localized computing couldn't offer?
Yeah, well, see, that's what got me into storage. Because when you are running and all you have is your own computer, then when the computer is up, you have access to your stuff. And assuming that the system was working right, if it fails and comes back up again, you haven't lost what happened before. But while it's down, you can't do anything. And you'd like to be able to have what's called availability, where you have access to your data even if a computer that you were using has failed. And the other thing is that you can have sharing on a wider basis, because I can share stuff with people at other institutions. We can be using our joint equipment to accomplish something.
Okay. So you have that kind of economy of sharing resources,
right.
And also this kind of redundancy, I can see how that would be very important for things
so
like
it was
banking.
really, this is why I got so interested in storage, because I thought this is it's a really another very important question. How do you manage to have storage that's online? This is storage in the cloud that what we talk about today.
Yes.
How do you make sure that the stuff you entrust to the cloud is actually what you wanted to do? That's the first question. And then if something goes wrong, how do you make sure it doesn't go away? So this is the problem that I started to work on in the mid-'80s. That led to the first of the protocols that was developed to provide reliable storage that's reliable and available. So that was your goal, always present, as long as not too many failures have happened.
Right.
Has the right behavior, even though there can be lots of people using it in parallel, and there can be failures happening. So the sort of reliability, availability, correct behavior, how do you get all of that to work?
So that project was that distributed database was called Thor? Is
No,
that
that
right?
was this protocol I'm describing is called Viewstamped Replication.
But it came out of this work on.
It didn't. It
It's
was just
totally
that
separate,
we
sorry.
were in asking this question: what can you get out of distributed systems?
Oh.
That's really the same question you asked, and this was one of the obvious important things you could get out of it. And at the time that I started doing this in the '80s, people didn't know how to organize what the right protocols were, so we started to work on this problem.
Okay.
Yeah.
Okay. And that protocol has become a more generalized.
It's a Leslie Lamport was also working on something he called Paxos.
Mm-hmm.
Leslie didn't know what I was doing. I didn't know what Leslie was doing. And nowadays, Leslie will say, I came up with the name, and she implemented it. So it was the same, basically
Okay.
the same system, yeah. And it was, my work was happening in the '80s. It wasn't until the late '90s that this stuff actually showed up in actual systems, when the Google file system came along and they actually provided a replicated file system with the right kind of behavior.
Well, this may be kind of a simple-minded question, but when I was reading about your work in this area, and distributed storage, distributed kind of databases, I wondered, what your thoughts were about all of this discussion about distributed ledgers and blockchains. As I just wondered what your opinion was of that whole area, since it does seem related to what you worked on.
Yep. So the first work that I did on Viewstamped replication only considered what we consider to be benign failures, which means the computer is either running or it's failed, or the network delivers your messages or doesn't deliver them at all, or if they've been corrupted, they're recognizably bad.
Yeah.
That was the Viewstamped replication. That was Paxos. In the '90s, I had a student, Miguel Castro, who was looking for a thesis topic, and I suggested to him that he look at the DARPA requests for proposals and see if anything interested him. And there was one in there asking for techniques that would help with the kind of malicious behavior that people were beginning to come up because the network was now out in the wild as opposed to just being in the small DARPA net thing that used to exist.
Right.
And he thought, why don't we see whether we can come up with a replicated system that will handle Byzantine failures? So Byzantine failures where somebody hacks into your machine and corrupts it so that it's no longer working properly, or corrupts your messages in various ways. And so that led to the second protocol that we invented, practical Byzantine fault tolerance. And that's what makes the blockchains work.
Really?
Yeah, I mean, what happened was the protocol that is in fact mostly in use today with all those miners is not a very efficient it has terrible energy implications, and it's also quite slow, and so people have been. The Byzantine fault tolerance doesn't have those problems, and it solves the same problem. So people have been trying in the blockchain world to sort of use Byzantine fault tolerance while maintaining this belief that the government is corrupt, you can't trust organizations. I mean, there's a sort of a libertarian philosophy
Very much
there.
so.
And whereas Byzantine fault tolerance is what's called a permission system. We assume there's a set of replicas that is pre-selected. It might change over time. You know, they're living in different data centers. They might belong to different organizations, but you sort of trust the group, and there's a sort of a lack of trust. So, I mean, you're absolutely right. This notion of a ledger, that's what Viewstamped Replication produced. That's what practical Byzantine fault tolerance belief produced. Cyber currency is not as hot now as it was a couple of years ago.
Right.
You know, it seems to me that one of the major steps forward in civilization was having currency that was backed up by governments. So I haven't been convinced about the virtues of cyber currency. I also am somewhat dubious about blockchains in general. I mean, logs are very useful, but I probably trust my credit card company to maintain the logs that have to do with my credit card, and I don't see why that needs to be pushed out of the company to a broader world. I do think that, in some sense, the log is the truth. I mean, I do think that's what you want. That's how they can prove to you that they've showed you the right, you know, current state of your bank account or
Right,
whatever. It's just
right.
that I think this, I don't actually believe in the unpermissioned stuff. I believe that there is a group of replicas that's maintaining the state for you.
Right.
Yeah.
And so would Byzantine fault tolerance be used in, you know, someone like a bank, you know, had to...
We hope they're using it.
But that would be the kind of idea,
Yeah.
you know, that you would use this. So you have, you know, the copies of every, you know, these multiple copies of your
That's
bank's
right.
books, you know, and, or like, you know, for a large bank.
Yeah.
Or, and in that case, yeah, it is permissioned, you know, you're
Yeah,
saying.
you have your various data centers, you
Yeah.
have your replicas, you know, you worry about stuff. You worry about what happens if somebody breaks into one of the data centers. What happens if somebody is listening and maybe can they detect your keys, because we use a lot of cryptography in making these systems work.
Right.
You have to think about stuff like that. There's a question about how many replicas do you want, how many do you need to make sure the system is secure enough. So
Right.
you do ask all those questions. But
Right.
yeah, I, you know, the thought that the Bank of England was going to have a bunch of miners in Siberia doing their basic log for them, it just didn't seem reasonable to me.
Okay. And forgive me if I didn't follow exactly. Were you saying that some of these blockchain systems, these cryptocurrency systems, they do use the Byzantine fault tolerance protocols?
In the
or-
research community, if you look at what's going on with the replication techniques,
Yeah.
they're trying to sort of combine that with the basic notion of unpermissioned
I see.
by selecting among the huge number of replicas by some technique that is not predictable in advance. The current smaller group that is making decisions about what the order is. And then they're changing this on a regular basis to try and keep ahead of any sorts of attacks that might be going on. The problem with Byzantine fault tolerance is, this is a fundamental issue, if your system is not going to work because there have been too many failures, is it going to fail safe or fail unsafe? Byzantine fault tolerance always fails safe, which means it stops working. And that's actually a problem if it happened. I don't know that it is actually a practical problem, because if you have enough replicas, machines come back up again and so forth.
Right.
But at any rate, you do need to worry about the systems out of commission for a while. So people are trying to think about how can we move stuff around so that we have a better, we have less times when the system as a whole is not available. So I mean, I'm not doing research in this area, so, but I am aware of some of the stuff that's been going on.
Right.
And people have been trying technically to look at this kind of problem.
Oh, that's very interesting. I wanted to talk about, unless I'm missing something huge. Oh, yeah, yes, sorry, yes.
You want some more?
I'm still okay.
Okay.
All I need is just a sip to keep going.
Unless it would be to skip over something that we should talk about beforehand, there is this period around, I think it was in 2000, that you took a leave from MIT.
Yes.
And went to work for a company.
Yeah, SitePath.
SitePath. Could you
Yeah.
tell us about that?
It was just, I thought, everybody was doing it. So I might as well try it. And I went to work for them. They were, honestly, I can't even remember what their product was.
It looked like it was to deliver video over the web.
Yeah, probably. At any rate, I tried it. I actually worked for them for a couple of years. They were bought by Cisco in the middle. And I like research better.
Was it too directed? What
It was
happening, or-
no, it really wasn't directed. I mean, I was sort of thinking at a very high level about what should be going on. But the nice thing about working in academia is that you have to find everything for yourself. Nobody is telling you what your research direction. So it wasn't that it was definitely more directed than I'm going to start this completely new, direction, which is what I can do. Yeah. But when I started, people didn't form companies like this.
Yeah.
And in the 90s, it changed. And, so now almost all my colleagues have companies that they started. So I was kind of curious about what it was.
So after you satisfied that curiosity, you came back to MIT.
Yes. Yeah.
And you returned to your work on distributed computing.
Yeah.
Yeah. I want to talk about when you moved over to administration, but I thought it might be helpful for people, just if we could give people a sense of like the ways that they might encounter distributed computing in their everyday lives, but not realize that it's distributed computing. What are some of the ways in which distributed computing affects our everyday life?
Everything we do is distributed. When you use your cell phone, that's a distributed system. When you use Facebook, that's a distributed system. Twitter is Google, everything is distributed. So a better question is, what do you use that's not distributed?
Wow, yeah.
At this point, everything is distributed.
Yeah.
Because whatever you're doing on your personal machine is backed up by the cloud.
Which is itself a distributed
Absolutely.
system.
Yeah, right.
It's just distributed
Yeah.
systems on top of distributed
Yeah,
systems.
absolutely.
Yeah, I think people, it's it's kind of like a specific term, you know, and people are much more familiar with these more marketed orienting terms like
Absolutely.
the cloud and
Yeah.
things like that. But it is true that all of that is
Yeah.
distributed.
You know, you have your
computing.
you know, your Kindle or your phone or your laptop, you know, or your iPad. And yes, that is a device, but that device is backed up by stuff that's not there. And so it's part of a distributed system. And then sitting behind the scenes is, in fact, some sort of complicated replicated algorithm like what we've been talking about that's making sure that all your data is not being lost and everything is hunky-dory. And yeah, so everything is distributed.
Thank you. Could we talk about when you decided to work as the associate provost for faculty equity?
So, okay, so what happened was I did feel a bit like I needed to give back. And when I came back to MIT, a close colleague of mine, John Guttag, was the department chair. And he asked me if I would be the associate chair. So the way it worked was EACS, a huge department, and we have EE and we have CS. And so at that point, we had a chair for the entire department, and then we had somebody in charge of EE and somebody in charge of CS.
Right.
And so I agreed to be in charge of CS. And what happened was, as head of CS, I was in charge of faculty search. I'd already been doing graduate admissions for years, but I was now in charge of faculty search. And so I set up my search committee, which consisted of people from there are sort of three major areas in computer science. There's systems, theory, and AI. So I had people, it was a small committee, but I had people from each of these areas. And I told them they should go off and talk to their colleagues and see if they could identify women and underrepresented minorities that we should be interviewing. And so they did this. And we identified a bunch of candidates, and we changed the rules a little bit. We decided we used to have certain schools that we would look at sort of preferentially, and people who didn't get their PhDs from these schools were maybe not so interesting. So we decided to ignore that.
Okay.
And I simply established the idea that if we saw somebody, a woman or underrepresented minority that looked interesting, we would make sure we had an interview, because you can't hire without interviewing. And as a result, over the 3 years that I ran faculty search, we hired 5 women when they hadn't hired a woman in the past 10 years.
Wow.
And it wasn't that we were finding people that weren't qualified.
Of course
In
not.
fact, the 5 women I hired have all done exceptionally well. I mean, I hired a lot of men too, and they have also done well. But it's, you know, it was not that we were scraping the barrel or anything like that. It was just that we made a point of looking or something. And so, so anyway, so that was an experience. And I also was on engineering council, which is all the department heads in engineering meet in this organization, which looks at promotions and who's being hired across the entire School of Engineering. And I discovered, you know, some things that I thought were not so great, like there was I forget which department it was, but there was a woman who was not going to be able to get tenure because she'd had such huge teaching assignments. And when I asked the guy, I said, how did you expect her to be able to do the research she needed to do when she had these huge teaching assignments? There was sort of no answer coming to that question. So I was learning a lot about what was needed to make affirmative action work better. And then Nancy Hopkins, who was the one who, are you familiar with what happened in the School of Science in?
No.
Okay, so at MIT in the 1990s, the women in the School of Science discovered that they were not being treated very well. They sort of each knew it individually, but they got together and they discovered they all weren't being treated very well. There's a documentary called Picture a Scientist that's come out. I think it's available on PBS. That shows what happened here and also some other stuff that's been happening. So they discovered things like they didn't have as much lab space. I mean, just a whole bunch of things.
Yeah.
And they wrote a report, and it had a big impact, not just at MIT, but sort of across the country as a whole. So anyway, Nancy Hopkins was the one who sort of started that thing, and she's a biologist. And she was acting as this head of faculty equity, and she got tired of doing it around about, I don't know, 2005 or something like that, 2006, and so she persuaded me to take it over.
Okay.
Which I sort of regretted. But anyway,
Because
and then that morphed into this position of associate provost, where I sort of built on what I had learned in running faculty search and put in place some new sort of ways that things were run, like you know, the idea that you have to interview if you're going to hire. So make sure you do those interviews. And also I went around talking to department heads and talked to them about their responsibility to junior faculty and how they you know, how women were more likely to say yes when men would say no.
Right.
So if it was not maybe a very desirable assignment, the woman would say yes, the man would say no. It was, you know, it was their job to make sure that these inequities were not occurring. And it was not that people were opposed to this. I mean, I think they were happy to get on board. It's just that they were ignorant. They didn't understand. So, you know, so I put in place some stuff.
So sort of informational culture shift, telling people about like the successes that you had in
Yeah.
hiring.
And
just
sort of, you know, what their
propagating that.
responsibilities are. You
Yeah,
know, that you're
right.
You're responsible for making sure that people have the ability, they have the time and ability to succeed. So.
And how did you feel? When did you stop doing that?
I stepped down when they got rid of the position, which I actually thought was a mistake. This was a position that had to do with faculty equity. And what they did is they folded it into a much larger thing, which was sort of equity across the whole institution, which I think just meant faculty equity sort of fell out. But at any rate, that was the end, and so I stepped out. Yeah.
And was that around the time that you decided to retire, or?
No, it was earlier than that, though I've forgotten what the year was.
Yeah.
Yeah.
Well, and you decided to retire around, was it 2012?
2014. I
2014.
retired.
I'm
Yeah.
sorry. And how did that change? What has that change been like for you and the pursuit of your interests?
Well, up until about 2 years ago, or maybe, I forget, it might actually have been a year ago, I was still doing research, but I don't have students anymore, so it always has to be with collaborators, and that stopped about a year ago, and I miss it.
Yeah.
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 Right. I still do some administrative stuff, so I'm not fully retired, but I'm thinking about whether there's a way to maybe, you know, I'm not leading my own group anymore, but I can participate in what other people are doing.
Of course.
Yeah.
Well, I did want to ask you about just some of the, just across your career, some of the most important, like who were some of the most important colleagues that you had that you either worked with directly or you thought their work was very, I don't know, sympathetic or important to you? Just some of the, I don't know, the close colleagues of yours.
So first of all, when I look back, I can see, though I wasn't really aware of it at the time, that people were looking out for me. So Bob Fano was the head of the department when I was hired, and he was always in my corner, even though I didn't know it. And Corby was too, and Jack Dennis was too, and somebody named Peter Elias, another EE faculty. I think those 4 people were watching behind the scenes, even though I didn't know it was happening. So I had these people in the back, you know, sort of helping me out. That was very important. As far as colleagues were concerned, my closest colleague at MIT has been John Guttag. John actually did his Ph.D. thesis with Jim Horning at University of Toronto. Jim was with me at Stanford.
Okay.
And didn't come to MIT until I think the early 70s. I keep forgetting. But he did his Ph.D. thesis on specifications for abstract data types. And then we started working together on this class that I developed at MIT about how to build big programs. And so we worked on that for many years, and somehow or other we just developed, you know, John was the one I became associate head for. I mean, we just worked together year after year after year. Even though we were running our own, you know, projects and so forth, we just worked together. I also felt very close to everybody in the systems group. I mean, we have a very strong, some of them I hired, but, you know, others, you know, came in before then. And, I mean, MIT I found MIT wonderful. I felt that I had wonderful colleagues. I enjoyed going to work every day. I had great students. It wasn't just the graduate students, you know, which I worked closely with on research. It was also the undergraduates who were interested in understanding things from first principles and really wanted to learn, you know, so it was just a great environment. And it wasn't that I necessarily collaborated closely with other people, but I just felt this collegiality that I thought was very important.
That's
Yeah.
great. Well, I think that exhausts my question list. Are there things that I should have asked you about that I neglected to?
Yes, you left out the Liskov Substitution Principle.
Oh my God, I did. I know I had that in here somewhere. I can't believe I must have just crossed it out in error.
Yeah.
That occurred, that was toward the end of the 1980s. Is that correct?
Yes.
Yeah, let's talk about that. Thank you so much for catching that. Thank you.
I mean, that's just, you know, it's such a funny thing. So at that time, I'd finished the work on Clue. I was working on Argus and also the replication stuff. And I was asked to give the keynote at UPSLA, which is the main object-oriented programming conference.
Right.
And I thought that this was a good opportunity for me to look into what was going on with Smalltalk and all the derivatives of Smalltalk that were developing out on the West Coast.
Right.
And so I started reading the papers, and I discovered that they were, of course, these were all languages with inheritance, but they were using inheritance not just for making an implementation that's sort of based on some other implementation but differs a little bit, but also for this stuff called type hierarchy.
Yeah.
So the idea was that you would write a program in terms of a type.
Right.
And they wanted that program to work even if the object that came in was a subtype, which meant it was a subclass of the class that implemented the type. And I discovered they didn't know what it meant. I mean, they just didn't have the rules that defined how type hierarchy could work properly. And the problem was that there was a sort of a tendency in that community to think in terms of implementation. So when they would describe a subclass, they would talk about how they didn't talk about behavior at an abstract level. They talked about how, oh, this implementation is like that one, but it differed in these ways. And this is what I think was getting in their way. They weren't thinking in terms of the interface and its specification. They were thinking more in terms of how things were implemented. And so I saw, papers were confused about this. So they wanted this type hierarchy, but they just didn't know what the right rule for how type should behave was to make it work right. And I saw a paper that said that, this is a little technical, that stacks and queues are both subtypes of one another. A stack is where you push stuff onto the stack and then you can pop stuff off. It comes out and the most recent thing comes off first.
Right.
A queue is you put stuff in sort of in order, and when you dequeue, you get the oldest thing off. So they're have very different behavior in terms of what comes on, how what comes off relates to what went in.
Right.
And so if you were writing some code in terms of a stack where you expected that the most recent thing would come off, and what was passed to you was a queue, this was not going to work properly.
Right.
But you only see this if you think in terms of specifications. You see this as a... So I came up with a description. I said, in order for type hierarchy to work, you need the subtype to behave like the supertype when used through the supertype methods. So
Yeah.
the subtype could have additional methods, operations.
Right.
But and if you wrote a program in terms of the supertype, you wouldn't be using those methods because you don't know about them. You only interact with the object through the supertype methods. And as long as the subtype acts exactly the same as the supertype for those methods, everything's going to be okay. So it's sort of like the weakest possible definition you could have. And that's what turned into the Liskov Substitution Principle, which is not a name I came up with. And, the story is that in the 90s, I got an email from somebody saying, can you tell me if this is a correct definition of the Liskov Substitution Principle? That's when I discovered the name. That's when I discovered there was, in fact, a very large group of people trying to understand the details of it, because it turns out it's important. It
Right.
actually makes this whole thing work. And then later I worked with Jeanette Wing to come up with an actual technical,
Formal
definition.
of it.
Yes,
Yes.
right.
Yes.
Yeah.
That's so interesting. So it again is almost like this.
Accident.
Well, not only
Yeah.
but no, it's kind of looking at this literature like you did for modularity.
Yeah.
Looking
Seeing
at,
where the problem was and being ready to find the answer. Yeah.
by taking a kind of a step back.
Yeah.
In a way, it's kind of that abstraction step and giving kind of a more formal characterization of
Yeah.
it, of this, to how to make, these structures based on inheritance
Yeah.
coherent,
Coherent.
Or avoid
Right.
pitfalls. Yeah.
Yeah.
That's very interesting. Yeah, I'm sorry I skipped over that. Well, maybe we could just talk for a few minutes just about your life outside of computers and outside of work in MIT. Have you kept up with hiking, or what are your
Okay, so for years, yes. At Stanford, I had some close friends. We used to go up to the Sierras for a weekend. We always went up to the high country, up to Tuolumne Meadows, and then when I met my husband, it turned out he was interested in this also. I honestly don't know how this happened, but so that was a very important part of our life. We did many vacations where we would do backpacking trips. I feel like I was very fortunate to have discovered that it was so beautiful up in the mountains. And things are not so good up there now with climate change and So yes, lots of that. I got married. I have a son. We did lots of traveling with him when he was young. We did also backpacking trips. He now works for Mitre. He got a Ph.D. He's a computer scientist, but he's a theoretician. He works in cryptography and stuff like that.
Okay.
Yeah.
Yeah.
And I have a granddaughter. You know, so I've had a very fortunate life.
Yeah.
Yeah.
Well, wonderful. Well, thank you. Those are all the questions that
Okay.
I had. Thank you so much for doing this with us. I really appreciate it. It's been
Oh, well, you're welcome. Thank you
delightful.
for traveling out here. I mean, this is a much bigger deal for you than it is for me to just come in.
It's a joy.